Hello everyone. So in this video, we'll see a very beautiful problem on the real analysis. Basically, it's depend on the parts of continuous of a function and Riemann integration. So the question is like this: that if f is a continuous function on the closed interval 0, 1 and integration 0 to 1 fx x to the power n dx equal to 0 for n equal to 0, 1, 2, 3, dot, 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 dot. So this means if we take the product of fx with the standard nth polynomial, say x to the power n, and taking derivative, that value is, taking integration, the value is 0 on the interval 0, 1. Then we have to prove fx equal to 0, identically 0 on the interval 0, 1. So to prove this theorem, we will basically use two important concepts one concept from the concept of continuous function, and other is a very important theorem called the weierstrass approximation theorem. Yeah, this is the idea. So before do this, so we need some extra work that we need to do. So let's some observation. So in the solution, the observation is in this solution basically. The solution. So let's say, so we have this condition. So let p is any polynomial. Let's say let px is a polynomial. Let's say summation r equals to 0 to, let's say, m degree m polynomial, and here we are taking ar x to the power r, where ar from the real number r. So we take any polynomial. So now we check the first observation. We will check that basically the integration 0 to 1, because it is clear. So fx into px of dx equals to 0. Why? Because you can understand this is why, because of the polynomial 1 x, x square, x cube are the basis for all polynomial. So that's why, and the integration is linear. So under, you can say, addition. So that's why this is 0. But we will prove it mathematically. So we'll check this. So how to do? So now let's write down here 0 to 1 fx into the polynomial px mean px dx. This is equals to integration 0 to 1 f of x. And what is px? Px is summation r equal to 0 to m ar x to the power r of dx. Now here basically we use a very beautiful theorem from the definite integral. So that is let me write it here, then I will tell you. So this is nothing but integration 0 to m. This is integration 0 to m, and then we'll take here integration 0 to 1. So this is fx and ar into x to the power r of dx. Why? Because of this, because the reason why, because since integration a to b f plus g is nothing but integration a to bf plus integration a to bg. Because of this, we can write from here to here. So now, yeah. So we move to the next page now. That so what we have now. So basically here we can, now if you go here, that you can see that you can factor out the constant here. So this will be summation r equals to 0 to m. Ar we factor out, then it will be integration 0 to 1 fx x to the power r of dx. Now see this part. By condition this is 0, so we getting summation r equal to 0 to m ar into 0. So this is nothing but 0. So what we are getting that just not this integrate the value 0 for x to the power n. It is still 0 if we take multiplication fx with any polynomial and take integration. So so let me write here. So we are getting that. So 0 1 integration 0 to 1 fx px dx equals to 0. This is true for all polynomial px from Rx. So this is the all polynomial whose coefficients are real number. Right. So now we'll state a very beautiful theorem. So here that let me write here the weierstrass that we will use now. Weierstrass approximation theorem. So this tells us that so this theorem has many version, but we will use here one version that I am studying here. So if f is a continuous function from closed interval a comma b to r is continuous, then there exists a then okay. So then for each epsilon greater than 0, for each epsilon greater than 0, there exists a polynomial, let's say called p epsilon x over rx. So here I'll tell you one thing. If you take the complex valued function, then the polynomial may be complex valued. So there exists a polynomial px such that now here this polynomial may not be unique. You can find out more than one polynomial such that fx minus p epsilon x, this absolute value is less than epsilon for all x belong to closed interval a comma b. So in graph you can understand like this. Suppose from a to b you have the function like this, and let you are taking and so epsilon neighborhood around this function, so like this. So then you can find a polynomial here basically, so something like this. So yeah, this way. So let me call this is the function fx, and this is fx minus epsilon plus epsilon. This is fx minus epsilon. So the red color is basically p epsilon x. Okay, so this is the idea. So basically if we have a continuous function on the interval a comma b, we always find out a polynomial. For every epsilon we always find out a polynomial such that the distance between the polynomial and the function is less than epsilon. All right, so now we are going to use this theorem here basically. So what is given? So choose. So let us select, or you can say choose epsilon greater than 0. So okay, so before go to the epsilon greater than 0, let me tell you one more thing that since here closed interval 0 comma 1 is compact because of closed and bounded subset of R, and f is continuous on closed interval 0 comma 1, so f is bounded on the interval closed interval 0 1. So that is there exists m greater than 0 such that you know the absolute value of functional fx, this is less equal to m for all x belong to closed interval 0 comma 1. This is very important here. We will use this, right? So now let us choose epsilon greater than 0. So choose epsilon greater than 0. Okay, so since by weierstrass approximation theorem, Weierstrass approximation theorem. There exists a polynomial, say px, in Rx such that the absolute value of fx minus px is less than epsilon divided by m. Okay, one thing here, why I am taking epsilon by m, you can understand after few lines. For all x belong to 0, 1. Okay, so now now you can say this is number 1 and this is number 2. So now if you multiple 1 with 2, multiplying 1 and 2, we get that absolute value of fx into absolute value of fx minus px, this is less than epsilon into epsilon divided by m. So sorry, so this is equals to, this is, we know this is m, so this is m into epsilon by 2. So now here observe that basically m cancel out, so that's why we took the epsilon by m. So we are getting, we know absolute value we can take inside here, so this is this minus fx into px, that absolute value is less than epsilon. So this is true because the absolute value of a into absolute value of b is nothing but a into b absolute value. So that's why we can write from here to here. Now we have this situation. So now we have a nice theorem from the Riemann integration that so that I'm writing here basically. We know that this is nice, that integration a to b gx dx is absolute value is less equal to integration a to b gx absolute value of dx. So here of course g is a Riemann integrable function on close interval a comma b. Then it is enough. If you take g Riemann integrable, then absolute value also Riemann integral, and this inequality holds. Okay, we know this is from the Riemann integration. Now you can take, this is the equation 3, right? So now we move to the next one. So now see the integration value, if you evaluate 0 to 1, you know here f square x minus fx into px, this function of dx, this absolute value is less equal to integration 0 to 1 absolute value of f square x minus fx into px absolute value of dx. And now we know this side absolute value, we know integration is linear, so integration 0 to 1 f square x dx minus integration 0 to 1 fx px of dx absolute value is less equal to, this is what we know. If you go to the equation 3, here we have the equation 3, take the integration both side of this, then what we get, then this integration will be less than 0 to 1 epsilon of dx, because this quantity is less than epsilon because of 3, so you can write by 3. Okay, so so this imply that now this is, we know 0 by this observation. This was the first observation that we did, so that yeah, this one, the observation, this, by this observation we can say that if you take any polynomial, then this value, you know, so you can say this is a star, that okay, so by star, so this is integration 0 to 1 f square x dx, and this is minus 0, absolute value is less than, you know, integration, this is epsilon x upper minus lower, by fundamental theory of calculus, by star you can say why this is 0. Okay, so what we are getting, we are getting that integration 0 to 1 f square x dx, this absolute value is less than epsilon. So now this is a positive integration, this function positive, integration is positive, so what we get, that we get integration 0 to 1 f square x dx, this is less than epsilon, and this is true for all epsilon. So let me write here, since epsilon greater than 0 is arbitrary, so integration 0 to 1 f square x dx is less than epsilon. So this is less than epsilon for all epsilon greater than 0. Okay, one thing I tell you here, that since we are taking integration, so this will become less equal. So this is less equal to. This is true, less equal to is for all epsilon. So we can conclude that that the integration value f square x, because see, so okay, let me state a very beautiful theorem. So not a theorem, just a statement, a logical. So this is true for, so we are getting that 0 less equal to integration 0 to 1 f square x dx is less equal to epsilon for all epsilon greater than 0. Now here see why this is greater equal to 0, because the f square x greater equal to 0. So the integration is greater equal to 0. Now we have a actually the, you can say, a statement we have that so this is the lemma, you can say, if 0 less equal to a less than, this is very trivial, for all epsilon greater than 0, so then a must be 0. This is very trivial lemma. So by this lemma we get, the integration of 0 to 1 f square x dx is 0. Now since f square is continuous, because f is continuous on 0 1, and f square is greater equal to 0 on 0 1, so you know the function f square x equal to 0 for all x belong to 0 1. So we getting that fx equal to 0 on 0 1. So we done. So basically here we used a fact that is the concept of continuous function and Riemann integration, that if you take a non-negative function and if the integration value is 0, then function must be 0. Why? Because geometrically integration means area. So if the function is positive, and if you have a point where the function is taking the positive value, then you get a small neighborhood around that point where you get a strip positive area. So then total area will be positive. That contradict, because you already considered that the integration value is 0. So that's why you have to take all value, functional value is 0. If you have this condition, then functional value must be 0. Okay, all right. So that concept we use, and one more concept, that is the theorem, weierstrass approximation theorem we have used. So these two theorem we have used this to prove this beautiful problem from the real analysis, because and this is basically a very good question for interview, like you can say the NBHM. So that's why it's a very beautiful problem. So now, so like similar, every day that we do that. Last time I'll give you a problem sheet here. So question. So try by yourself. Problem. Okay. So this is now I'm telling you here the problem that basically. So suppose everything is given. F is continuous. Let's say on 0 1, and integration 0 to 1 fx x to the power 2n dx equal to 0. Instead of taking for all n, we are taking only even 2n equal to 0, where n equals to 0 1 2 3 dot 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 dot. Is it possible f equal to 0 on 0 1? So you guys try this problem, and thank you. So see you in the next video. I'm going to stop here. See you in the next video.